Next, we tried the commutator as a propagator or something like this. Well, what we did is that we asked the question that what do we really want to know? What we want to know is that if we make two observations of two field operators, which are in space-like separation, would the observation of one operator influence the observation of another operator? So in other words, we want to consider what this object is for x and y space-like separated. So by the way, in a previous lecture, I argued that this is what we should consider, but I was wrong. It's actually we actually have a more stronger statement. It is just the commutator that we should consider. And why is that? Because we know from uncertainty principle that if we have two operators which do not commute, say A and B are operators which do not commute, then the observation of A and B will yield an uncertainty relationship which is not going to be given by 0. So this will be something like, and I think there's a factor of half here. So it's only when A and B commute that we can say that the product of in the uncertainty of A and uncertainty of B is going to be 0. So if we can show that this is 0 for space-like separation, that quantum field theory is a causal theory. That's what we want to establish. So let's just do this. So this is, we are the commutator of x, phi of x and phi of y. We can go to Fourier space, and then we will get two integrals, one on k1, one k2. And then what we will get is that from the Fourier expansion of these two operators, we will get 4 commutators. But of those 4 commutators, 2 commutators will vanish, and those will be the commutators of 2 creation operators and commutators of 2 annihilation operators. But what will survive are commutators of an annihilation operator and a creation operator, and they will have an exponential factor of this form. As well as a commutator of a creation operator and an annihilation operator, and that guy will have an exponential factor of this form. Now we can use the canonical commutation relationships and do the integrals. And if I do the integral, then I get, when the dust settles, and by this time in our course, I expect you to be able to do this integral very quickly. If not, then you need to go back and practice. Otherwise, you will not do well in the exam. So this is the expression for the commutator, and this is given by dx minus y minus d of y minus x, the 2-point function, the function that we observed before. So now what we want to do is that we want to take x and y to be space-like separated. If x and y are space-like separated, then what we can do is that we can always take x minus y, apply a Lorentz transformation, a continuous Lorentz transformation. So there's and rotate that into minus of x minus y. And if I look at the picture, space-time picture, it looks something like, so this is x, and this is the light cone of x, and y is space-like separated, so y is somewhere on this hyperboloid. Then what we can do is that we can just make a Lorentz transformation which takes y 2 minus y. And therefore, this thing goes to this thing. So because there's a continuous Lorentz transformation which takes us from this to this, that means that this sign flips over here. And then we have, we have the same two factors. And therefore, we get 0. And this becomes 0 only if x and y is space-like separated.